Modern enterprise databases process thousands of transactions every second. If two users attempt to modify the same piece of data at the exact same millisecond, the system risks total corruption. To prevent this, database management systems act as traffic controllers, using a mechanism called locks. A transaction must acquire a lock on a piece of data before it can read or write it, ensuring safe, isolated access. You can see the scale of the problem in this wide view of a sailing fleet. Imagine a database engine treating every individual record as a distinct, lockable unit. This micro-level approach allows maximum simultaneous movement. Thousands of independent updates can happen side by side without colliding. But scale exposes the flaw. If an analytics transaction needs to read a table containing 10 million records, the system's lock manager must track, grant, and release 10 million individual locks. The computational overhead of managing those locks eventually exceeds the cost of executing the query itself. Alternatively, a system can take a macro-level approach, locking an entire file or even the entire database as a single unit. The lock manager only has to process one request. The trade-off is immediate. Because the entire dataset is locked, every other transaction in the queue halts. The system creates a total bottleneck, where the entire fleet must idle in the water, waiting for a single vessel to finish its route. Database architects are forced to navigate between two extremes. They need a protocol that provides the low overhead of macro locks when dealing with large datasets, while maintaining the speed and concurrency of micro locks for single record updates. The solution to this paradox is the multiple granularity locking protocol. It allows transactions to adaptively choose the exact scale of their lock based on the work they need to perform. The protocol organizes data into a nested tree. The database root branches down into areas, then files, terminating at records. This structure enables implicit locking. Locking a high-level node, like a file, automatically locks every record inside it. The engine no longer needs to grant millions of distinct record locks for a table scan. A single high-level lock achieves the exact same security, drastically reducing the burden on the lock manager. However, nesting creates a structural trap. If a transaction wants to lock an entire file, the system must first guarantee that no other transaction is currently holding an exclusive lock on a specific record buried deep inside that same file. The system requires visibility. It needs a mechanism to instantly determine if a conflict exists deep in the tree without having to inspect every single leaf. Look at this specific sailboat featuring a red stripe on its mast. In database terms, assume a transaction has requested and received an exclusive lock, an X-lock, on this single specific record to perform an update. While that update is happening, a new transaction enters the system. It needs to run a full system audit, which requires placing a macro-level lock over the entire fleet. The system cannot grant the macro lock. Doing so violates the isolation of the red-striped boat undergoing an exclusive update. To detect this collision, a naive engine would scan the entire tree, checking every single record until it stumbled upon the locked boat. In computer science, this is an O of n search. The time it takes to check for a conflict scales linearly with the number of records. In a database with billions of rows, an O of n search for every lock request is computationally catastrophic. The engine cannot afford to dive deep into the tree every time a lock is requested. It must pull that status information up to the surface. The protocol solves the ON search problem by introducing intention locks. These are top-down markers placed on parent nodes to signal activity occurring deeper inside the hierarchy. First, the intention shared lock, IS. To read a record, it leaves an IS flag on the root as a read warning. Second, the intention exclusive lock, IX. To modify a record, it places an IX flag on the root, signaling a write warning below. The third is the SIX lock, shared and intention exclusive. A transaction uses this when it needs to read an entire file, locking it in shared mode, but also intends to update a select few records within it, flagging them as exclusive. Intention locks reduce an ON search down to O1. To determine if an entire file can be safely locked, the system no longer inspects the records. It simply looks at the file node. If an intention flag is present, the system knows immediately that a conflict exists below. By forcing every transaction to chart its path before it acts, the protocol coordinates thousands of operations without ever losing track of a single record. These warnings only function because they adhere to strict mathematical rules defining which locks can exist on a node simultaneously. For example, multiple IS and IX locks can coexist on the same root node. They simply indicate that multiple transactions are operating inside the database at the same time, likely updating completely different records in completely different files. This logic is mapped in the lock compatibility matrix, evaluating IS, IX, shared, 6, and exclusive states. If a transaction holds a shared lock and another requests an IX lock, the matrix evaluates to false. The second request is blocked. The protocol also enforces directional strictness. A transaction must acquire its locks purely top-down. It secures the database root, then the file, and finally the individual record. Once the operation is complete, the locks must be released purely bottom-up. The record is unlocked, then the file, then the root. The matrix serves as the ultimate logic gate. It rapidly filters incoming requests, ensuring that conflicting operations are delayed and compatible operations pass through unimpeded. We can now trace the full protocol inside our steady-state fleet. Transaction 21 enters, requesting to read a single boat. It acquires an IS lock on the entire fleet, then an IS lock on the specific sector, and finally a shared lock on the boat itself. Simultaneously, Transaction 22 enters to repair a boat in a different sector. Because IS and IX are compatible at the top level, Transaction 22 places its IX lock on the fleet and proceeds without delay. A third transaction attempts to lock the entire fleet for maintenance. Instead of scanning the water, it checks the top level, hits the IX flag, and is instantly delayed. Data integrity is maintained with minimal processing overhead. The system can also optimize itself dynamically. If a transaction begins updating hundreds of individual boats, acquiring hundreds of separate microlocks, the lock manager will recognize the strain. Through lock escalation, it will trade those individual locks for a single exclusive macro lock over the whole sector, instantly reclaiming memory. The multiple granularity locking protocol delivers concurrency precisely because it respects the architecture of the data. By utilizing nested structures, deploying intention flags, and strict compatibility math, it allows the database engine to adapt its overhead in real time, securely orchestrating operations at any scale.